Okay, I think it's time. Good morning, everyone, or good afternoon. I'm Cherry Kubota. I'm a professor at the Ohio State University. With me, my graduate student, John Ardo, moderating together for today's Indoor Ag Science Café. So if you are new to this space, welcome. This is a space for learning and then also exchanging information. The whole project is funded by USDA NIFA Specialty Crop Research Initiative. We are in the middle of 4th year, I believe. And then the project team include me and then also my colleagues, actually led by Michigan State University, Dr. Eric Ronco, and co-directed by myself. And then also Carrie Mitchell, Purdue University, and other investigators are in also Michigan State University and Purdue University and University of Arizona. So this is geared toward indoor vertical farms. And then again, for understanding better and then information exchange. So with that, I'm going to hand it to John to do a future cafe information and introduction of today's topical presenter. All right, John?
All right. Hello, everyone. It's good to see you all here today. Thank you for coming this morning. So upcoming in the Ag Science Cafe, we have a few things to go over. So in the upcoming cafe series today, we'll hear from Dr. Shamim Ahamed, and then in January, we'll hear from Dr. Harry Berman talking about introducing spinach and hydroponic crop production. And in February, we'll hear from Dr. Kubota herself about low pH hydroponic nutrient formulas for growing leafy greens to better manage root rot disease management. You can find all of the OptimIA events on the website up in the top right corner at scri-optimia.org, and you'll be able to find all of the upcoming cafe series there. And I encourage you, if you're not already, to get on the email list so that you can hear about all of these updates directly from us.
Just wanted to mention, so this semester, we intentionally picked a lot of engineering or more non-plant science type of topics. I'm trying to go back to a little bit more plant-based information next series. We still have few open slots available. I am interested in having industry talks rather than too many academic people speaking, but let me know if you wish to talk or if you want to have someone you wish to listen to. So I just wanted to mention that. Thank you, John.
All right. Something else we'd like to draw your attention to is the recent updating of the OptimIA University website. So you can find this at optimiauniversity.org. And essentially, we're trying to build a repository of basic knowledge for indoor farming. So everything from the basics, the background, indoor farming systems, plant responses to environmental conditions, production management, economics. There's a lot of really good information here. And so I encourage you to visit that site and review some of that material. And I believe we are still updating with more presentations, but you'll hear from a lot of the leading experts in these various fields about different topics that are very relevant to the indoor farming space. So I encourage you to visit that website whenever you can and review some of that content. As for today's agenda, we're going to have two parts. The first is going to be a presentation from Dr. Shamim Ahamed, who's from UC Davis. He'll talk about his presentation of the potential of fault detection and diagnosis tools for autonomous CEA production. At the end, we'll have an open discussion. The part two of today, the open discussion will not be recorded, but the presentation will be recorded and will later be posted both on our website and on YouTube. So you are able to find this presentation after today. So with that, I'm going to end my screen sharing. I'm going to turn it over to Dr. Ahamed, and you're welcome to begin your presentation.
Okay, thank you, John. And let me just share my screen first. Okay, so good morning, everyone, and thank you, Dr. Gupta, and your team for inviting me to give this talk. As John mentioned, like today, I will try to give talk on the potential of fall detection and diagnosis tool for autonomous control environment, agricultural production, and this is Shamim. So I'm working in UC Davis in the Department of Biological and Agricultural Engineering. Today, the talk I will give mostly trying to focus the very fundamental things. What is fault detection and diagnosis tools? And what could be the possible application in the Control Environment Act? And mostly like this is not that much very common in Control Environment Act, but it's very common for very complex control system like the building or any industrial process application, and even like very high application like the aerodynamics case, like for the flight monitoring, this kind of case, this kind of tools is kind of very common. So for this talk today, I will just try to give some kind of very fundamental things about the Control Environment Act and why we should think about the fault detection and diagnosis tools could be an option for the Control Environment Act automation. And then just kind of very brief about the fault detection and diagnosis and some of the application or the research we have been done for the building industry and also some other research that so far I found in the Control Environment Act and some of my ongoing research activities that we are doing related to the fault detection and diagnosis for Control Environment Act production. Now, so if I just okay. So just kind of very brief things about the global market of the Control Environment Act. We know like the Control Environment Act industry is kind of very booming, like, and it's expanding like just from two different aspects. Like if we just talk about the conventional greenhouse market and also the intervertical farming, and we can see that the expansion is definitely for the intervertical farming is higher compared to the greenhouse, but the overall expansion is kind of very high for the Control Environment market. So this is also, we try to, another data that we try to collect from the different sources, and we try to plot in that things where this market growth is kind of more exponential, and we can see the North American market is definitely at better high rate compared to the rest of the part. It's just expansion rate. It's not the current statistics or the data. Now, just if we talk about the US market, and we can see and the different part of the USA for two different aspects, like conventional greenhouse or intervertical farming market. And again, this is the data from 2017, and definitely this number, it could be slightly different or in current time in the United States. And this kind of showing that what are the different the Control Environment structure, like the 47% the glass type greenhouse, and around 30% is the intervertical farming, and rest of them are the low-tech greenhouse, container farm facilities. And this chart is kind of showing the distribution of those kind of facilities. Either we can see almost close to 50% is located in urban area, and the rest of them are suburban or the remote area. And in that perspective, mostly the greenhouse is slightly remote area, but mostly the intervertical farming of the container farm are located in the urban or suburban area. So those are kind of just a very fundamental thing, basic information about the CEA, their market, and also the expansion. So now they have different challenges in the Control Environment Act. One of the big challenges is the high operational cost. So this is one of the data from my PhD studies. Like we try to see the breakdown of the operational cost for greenhouse in cold region in Canada, and we can see the labor and the energy cost for the lighting, heating, or the CO2 is one of the biggest component. And then for intervertical farming, like I think this is one of the common data most people use, like what are the energy breakdowns or the operational cost breakdown for plant factorial intervertical farming. And we can see the 28% is mostly energy related cost, and the labor is almost the same number. We can see like close to the greenhouse And from that perspective, like from this energy cost, we can see almost 70% of that energy cost comes from the lightings, and around 28% or 30% energy cost could be because of the air management. That's mostly kind of linked with the heating, ventilation, air conditioning system. So now, like you can see that the operational cost is one of the biggest challenge, and that operational cost definitely we have to kind of reduce to see this industry as a sustainable from economical perspective and also from the environmental perspective. Now, if we just talk about the future of the built environment for the CEA, we can see that from greenhouse perspective, these greenhouses are becoming like kind of big. Like for example, the FR based from Kentucky, like they have 60-acre greenhouse, and also like if we just see the second figure, we can see the rooftop greenhouse also kind of could be a couple of hectares. This picture is from the Loafer farm in Montreal. So that means like our CEA industry becoming large, and in that perspective, we are kind of have large number of the sensor that has to be integrated, and that's kind of making our system more complex. And it's very common that this kind of sensor could give you the wrong information, and that could kind of lead to the inaccurate control system, and that's going to be a big challenge. And even in future, like this could be the future of the CEA, and I know like this is very concept level. But again, so if we see that our CEA market is kind of expanding or like kind of being this kind of very complex built environment, then definitely the autonomous is one of the biggest requirement. And at the same time, for doing the autonomous, a large number of sensors integrated, and our control system is mostly driven by the data from the sensor and others different of other control system like actuator. Now, like if any fault happen, that's kind of becoming more complex. And that's why we think that the fault detection and diagnosis has a huge application for the CEA, as like the system is becoming more complex and many sensors are kind of being integrated. This is kind of showing that like if we have a multi-storage the intervertical farming, and you can see they have the multiple sensor and the actuator is kind of involved. And that's why like we think that the fault detection and diagnosis tool has a huge potential. And also like when you talk about the cyber physical system, that's also kind of becoming the system more complex for the CEA. And in that perspective, also many sensors kind of being required to kind of make the cyber physical system as a kind of the application for the CEA. So from that perspective, I think we believe that the fault detection and diagnosis tool has huge application to kind of minimize the problem that's occurring from the wrong information from the sensor. So now I will just give you kind of very fundamental things like what is fault detection and diagnosis. So it's just from the name, you can just kind of get a very clear idea. Like, for example, if any system is kind of not working exactly based on the set parameters or based on our expectation, definitely we have to identify that problem. And finally, we have to diagnose that what is the root cause of this problem. So from that perspective, like the fault detection and diagnosis is software tools basically use to discover the system problem and also identify the optimization opportunity before they kind of being very extreme, like kind of very false, like the kind of the alarm system or any kind of excessive waste of the resources like the energy and the water use, especially for the control environment perspective. So that's kind of the tools that are available for mostly for the building and other industry. But for the CEA, like we don't have that kind of tools, and we need kind of more research and development from that perspective. So how it's kind of like you can imagine any fault detection and diagnosis tools is kind of closed loop. So if you have any fault, that system will detect that fault, and when you detect that, you have to identify that fault. And based on that, you have to diagnose what are the root cause of this fault. And after the evaluation and analysis, the monitoring system will kind of take the new action, like either these faults need to be kind of repaired. If it's the sensor fault, either the sensor needs to be calibrated or the sensor needs to be completely replaced because of the physical damage or other big problem that's basically causing the wrong information for the sensor. So from that perspective, like fault detection and diagnosis perspective, like there is 3 different terminologies commonly used. The first one is the feature generation. The feature generation is the very critical for developing any fault detection and diagnosis tool. The reason is that for most complex control environment system, sometimes some of the parameters could be under monitor, or for example, as I mentioned, the big facilities, there might not be enough number of sensor to kind of get the uniform representative data from that system. So from that perspective, like you have to analyze the existing operational data alone to kind of make some more information from the data to kind of make a reliable decision. So that's basically kind of, you can imagine like whatever the data you have, based on the data, like you can kind of generate more information for the decision making. So the feature generation usually kind of a physical relationship between the data that you have and kind of make some new correlation with some other parameters that was not monitored or was not available in the control system. And it could be also kind of based on the domain knowledge, and some statistical model also could be used to extract the more information from the operational data. So that's basically the first step for developing any fault detection and diagnosis tool. The second part is usually called the fault detection or the symptom generation. So this perspective mostly involves the operational data and also the feature that generated from the previous step for identifying the anomalies or the fault. So this fault detection or the anomaly detection could be performed with some linear discriminant analysis or rule-based things, like based on the domain knowledge. And based on that, like some of the anomalies can be further identified to create the symptoms for further diagnosis and evaluation, especially the next step is the diagnosis. That means like when the fault is detected, then you have to think about like what kind of symptoms it can generate that will give more information to diagnose that fault. From diagnosis perspective, this step basically kind of use the feature generated from the first step and also the symptom generated after the fault detection. And based on that, like you can kind of look at that where this fault is exactly happening and also isolate the root cause of that fault. And that information is kind of sent to the further analysis or in the feedback loop to make the decision that what kind of action need to be taken to solve this issue that causing for the control system. So what are the common types of the fault that we can expect for any kind of control system? The most common fault could be from the sensor related things or could be the actuator or some mechanical fault, but the sensor fault is the common and kind of very critical to detect. So this diagram is kind of showing a kind of representative things about a control system. If you can imagine, this is the greenhouse. So, and from that greenhouse, like you have the different control input, like what will be the temperature, relative humidity, or other parameters. And if the system has some kind of some faulty effect, like it could be because of the environmental factor, could be because of the itself, the sensor calibration related fault, and that will give some wrong information. That means if y is the actual value, the dy is kind of the additional error is added to the system. And based on that, if you run the control system, it's basically either you are wasting the energy or you are running the control system in a wrong way based on the wrong information the sensor is giving to you. So as I mentioned, like the sensor, the fault could be, this could be sensor fault, could be actuator fault, either mechanical or electrical. The plant or process related fault could be some structural fault, also could be the software or the networking fault. So today in this talk, mostly we'll try to kind of keep focus on the sensor fault and the actuator fault. So now if we talk about the sensor fault, like basically 4 different types of the fault is very common in the sensor. It could be the bias fault, drifting fault, completely failure, or the precision degradation. These are the 4 different types of the fault is very common. And sometimes also another types of the fault could identify, it's called the calibration fault. So now this diagram is kind of give you an idea like how the physical system and automated fault detection and diagnosis system is kind of works. Like for example, like you can imagine in the greenhouse, and in that perspective, this is the physical system. So if any fault is happened, that means the systems will behave the different way than the expectation. And if that is continue, like for example, if you have some the sensor is not working and it's giving the wrong information, and based on that, if you run the control system, and after long times, it will give the symptoms that basically show the ultimate effect in that physical system. So now how fault detection or automated fault detection and diagnosis system works. So it could be based on the information from the sensor, and could be also observation from the growers inside the greenhouse. And based on this data, as I mentioned, the first step is the feature generation. So you will try to kind of derive more information that you can generate existing the data from the sensor or the knowledge base or the domain information. And based on this feature, like you will try to detect that fault, like where is that fault is happening, either is a sensor fault, actuator fault, or if it's sensor, like what kind of sensor fault is happened. And if you can detect, then the next step is kind of some symptoms definitely will show up because of that fault operation. And finally, you have to kind of classify or diagnose that fault. What kind of fault is that, and what are the root cause that kind of causing this problem? And then finally, you have to say that, okay, this is the particular fault, like either the sensor is completely physically damaged, or somehow the sensor, the data that is giving needs some calibration. And based on these things, the control system basically works. So now this diagram also kind of showing you like the complete process that's kind of required for the fault detection and diagnosis. So you can imagine like kind of for any commercial or residential building, what could be the data source? It could be the human itself, as I mentioned, the observer inside the building, or even in the greenhouse. Then another is called the building automation system. The same things also applicable for the control environment ag. We have you can call the control environment ag automation system. So there is another 2 other systems that's common in the building. And as I mentioned, like our control environment ag industry is kind of going to in that trend, like kind of big commercial and residential building. From that perspective, definitely we need the building information management and also the building energy management system. So these are the kind of the data source for fault detection and diagnosis tools. So based on that, I think the next step, as I said, you can generate the feature based on the building data from the building automation system, building information management, and also the building energy management. So from that perspective, you can have the different way to kind of generate the feature. It could be the statistical model, qualitative model, and also the black box, gray box model, and also the white box model. I will give some idea in next slide, like what are the kind of the gray box, white box, and the black box model, like just kind of if someone have some confusion about this terminology. Based on that, like if you use that model, that will give some kind of the feature that you can generate. And based on that feature, again, like as I said, like the next step is the fault detection. And based on that fault detection, you have to kind of finalize like what are the symptoms you can generate and diagnose that fault. Finally, that's basically give the signal to the control system. These are kind of giving a complete picture how the workflow happen in fault detection and diagnosis tools. Now kind of some general information. So if you have any fault detection and diagnosis tool, what are the metrics that you can use to kind of evaluate the fault detection and diagnosis tool. The most common metrics usually used is called the false positive rate or the false negative rate. And sometimes other additional terminology is also very common to use to kind of evaluate the performance of the tools, like the precision, the true positive rate, and also the detection time. So basically, based on these 4 or 5 different metrics that are used, like you can kind of evaluate what the performance of the algorithm or the fault detection and diagnosis tools that is developed or integrated into the building control system. So as I mentioned, there is no clear methods to determine which metrics you should use, but there have some guidelines. For example, if you have any minor fault with localized impact, you should prioritize the minimizing the false positive rate. If you have more critical fault on the equipment levels, then you definitely need to prioritize to minimize the false negative rate. And also at the same time, you should have the low occurrence of the false positive below acceptable frequency. If you have like kind of very complex related to the fault that's related to the safety related issue, in that aspect, you definitely need the detection time, and also the false negative should be minimized, because like if you have any safety related fault from that perspective, you need to identify that things as soon as possible to kind of avoid any big accident or any kind of major like problem in the system. So from that perspective, the detection time is one of the biggest things you have to think, like how fast you can detect that fault. So another metrics also used mostly from the research perspective. It's called the receiver operator characteristics. So this is kind of the relationship between the false positive rate and total false rate. So that kind of give you an idea, like the different tools that you develop or the different types of the fault detection and diagnosis you are considering to integrate in the building automation system. That will give like which one is kind of the more close to the optimal level. For example, in this graph, we can see this is kind of more ideal case, and the others, method 1, method 2, and 3 kind of deviated from the ideal case. So that's kind of will give you more information from the research perspective, like which algorithm you should think will perform better compared to the other tools or the algorithm that you are considering. So now I will just give you some very basic information about the different models that usually use for fault detection and diagnosis research. As I said, like generally we can classify this model into 3 different groups: the white box model, black box model, and the gray box model. So then I will also give some idea in the next couple of slides, like the different application of this model from our research and some of the research from the reference. So in general, the white box model is mostly from the like kind of the law of physics, or you can say that like if you can develop any model that based on the mathematical procedure or based on the law of the mathematics, then we usually call the white box model or the first principle model. The black box model is kind of completely like, as we know, like any machine learning algorithm or any kind of statistical model, that's basically we can define as a kind of the black box model. And the gray box model is kind of the combination of the first principle or the white box model and also the gray box model. And I will show also some example of the gray box model from our research. Mostly this kind of model sometimes is required. Definitely our goal is like always to focus that either the system can be modeled with the white box model, but sometimes some part of the system could be very complicated with the white box. Then we try to apply the black box. Then in combination, we can develop the complete system model, and that usually defined as a kind of gray box model. So this chart is kind of also give you an idea like the different types of the model that the use for the system analysis. As you can see, any kind of white box model is basically you can analyze every part of the internal component of the model. But as I said, for the black box, if you don't know the internal component, and the gray box model is kind of in between these two. So the part of the white box component and part of the black box model are kind of integrated together to kind of detect or simulate the unknown parameters for the whole system level. So now I would like to give also another fundamental information. I think we need to also kind of give that information to kind of get clear idea, like what are the application of fault detection and diagnosis. So usually we call the commissioning things, and this is very common for any kind of the physical system that we have. We usually do the commissioning. So this commissioning is basically doing to kind of see that the way we are expecting for that particular system, either it's working in that based on that design and the guidelines that we expected, or we kind of selected for designing that particular component. So usually it's called the commissioning, and there is another call is the retro commissioning. So the retro commissioning usually done for the existing facilities. So for example, after completing the whole facilities, like after operation, and if you like to kind of analyze that, like how this existing facilities is working, and then from that perspective, the final step is the ongoing commissioning. So the ongoing commissioning is mostly kind of to do some analysis or some feedback system based on the data from the building system or any kind of control environment like facilities. You can do some continuous analysis and kind of identify that any problems that the building exist and what could be the possible optimization things you can do. So now I'll just give you a data like why we think that the fault detection and diagnosis is important for the control environment ag. We don't have any data for, especially for the CA, but we can show the data from the building sector, and we can kind of get an idea like how much the energy that we can save in the control environment ag facilities. So some research showing that almost 20 to 30% of the energy waste in commercial building because of the wrong information the sensor is giving, and the control system is operated based on that wrong information. That's a huge number that could be saved with some fault detection and diagnosis tools. In CA, definitely we have the energy is one of the biggest concern, and also the faulty data is very common in agricultural application compared to the others case like the commercial or residential building. So from that perspective, that has huge opportunity to kind of save the energy and other resources that use in the CA facilities. And the automatic ongoing commissioning with the fault detection and diagnosis definitely could save that energy that's wasted because of the wrong information from the sensor. And this chart is kind of give you an idea like how the different commissioning things like from the without retro commissioning, just to kind of we don't do any kind of commissioning things with the fault detection and diagnosis tools. That will be the energy demand. Now, if we just integrated the retro commissioning, so you can save the energy after this. And if you do the automated ongoing commissioning with the fault detection and diagnosis tool, you can save more energy that's being wasted because of the faulty data the sensor is providing to the control system. So now if we talk about the fault detection and diagnosis in the building or the energy saving, this graph is kind of showing the complete feature, like how the fault detection and diagnosis works. So like, for example, if you have any heating, ventilation, air conditioning system, it's providing the data about the building, and based on this data is kind of stored in the building management system. And using that data, like you can develop fault detection and diagnosis tools. And if you integrated that fault detection and diagnosis tool in online monitoring system, based on the feedback, you can kind of more precision way, you can control the heating, ventilation, and air conditioning control system. And this is also kind of one of the reasons from Mr. Barkley, they did like how this fault detection and diagnosis tool could save the energy in a building. And you can see the energy save could be up to 30%, and depending on the types of the building and the facilities, and how much energy per square feet you can save with this fault detection and diagnosis tools for the building. And this graph is kind of showing the advantage of the fault detection and diagnosis in leak HVAC system. So definitely, as I said, the energy saving is one of the biggest things. The cost definitely will be saved. And also like the more efficient way you can provide the control environment that's required for the equipment in control environment ag case. This will be the efficient way we can provide the temperature, relative humidity, CO2 lighting for the plants. So now I will just give you a couple of quick research that we did and also some other study did, like the different algorithm development for the fault detection and diagnosis. So this is basically we did for this research for the building, and this graph is showing a building air handling unit. You can see the return air is coming, and that return air could be exhaust or could be mixed with the fresh air. And then we have the heating coil, humidifying coil, and the cooling coil that's basically giving you the control system. So in any CA facilities, especially indoor vertical farming or fully closed greenhouse, this kind of the air handling unit is very common, and large number of sensors is kind of being integrated with this air handling unit. So, and it's very common that this sensor could provide a wrong information. And based on that, like if you run the control system, this supply air temperature will give the wrong information. So we kind of generate those data from the building management system, and we use this data to develop a virtual sensor for air handling unit. And that virtual sensor could be used as a kind of the calibration tool for the existing physical sensor, or it could be kind of used as a complete replacement of the existing facilities. So for any kind of model development, sometimes you have a large number of sensors. First, we try to kind of analyze that what kind of the input variable is most critical, and also remove some redundant variable. So we did some Pearson correlation analysis to kind of identify the most critical parameters, and sometimes some of the parameter has kind of the redundant information, and we try to minimize those input variables. And based on that, like as I said, like this is basically we developed on the gray box model for developing this virtual sensor. The first part is basically we try to model the temperature change from the heating coil and cooling coil, and we use those part is very complicated, and we use the data driven model to kind of predicted the temperature change from the heating and cooling coil component. And the next part is basically our goal was to predict the supply air temperature, and for doing that, like we need to also do the temperature modeling for the mixing box that I showed in the previous slide, where the return air is coming and mixing with the incoming air. And that graph is kind of showing that how this gray box model can predict the supply air temperature compared to the measured data. So, and this is kind of giving you the statistical parameters, like how close this model could accurately predict the supply air temperature. And if, as you can see, the accuracy is kind of quite good. And from that perspective, this kind of virtual sensor algorithm could be integrated into the control system to kind of do some self-calibration of the sensor. And in some case, it could be also complete replacement of the physical sensor. And we also try to develop some the machine learning algorithm, and we try to compare with the gray box model and also multilinear regression model. And we can see that the artificial neural net model or the deep learning model is kind of outperformed compared to the gray box and the multilinear regression model. So now I will just give you a quick overview of the different application of the fault detection and diagnosis for greenhouse application. Some research so far done, like most of the research was done in around 2000, like 1995. The first research I found in the greenhouse case, the fault detection and diagnosis was done for greenhouse sensor. This research basically tried to analyze the faulty information for the indoor temperature sensor, and they just used the flash flex artificial intelligence model. This time that was kind of the way they did, but right now nobody is kind of using this kind of algorithm. And this kind of chart is showing that like what is the expected result, like when the fault basically actually practically happen. and that algorithm, either its fault is detected or not detected. The second research also kind of done around, as I said, 2000, around that time. They use mostly the white box model, the knowledge-based model to develop the fault detection and diagnosis in greenhouse application. And they kind of try to identify the indoor sensor, indoor temperature sensor, the relative humidity sensor, the outdoor sensor, and also the ventilation fan, either it's working or not working, and also the floor watering, like especially for hydroponic, like either it's working or any kind of problem is happening in the hydroponic pump control system. So you can see this graph is kind of showing based on that algorithm, like either like when the fall is happen, you can see like the initially, like you can see like it's not like kind of expected result for the algorithm is giving compared to the sensor data. But after, like, for example, like after the 8, like you can see like there have some anomalies between the sensor data and the algorithm data. And that's kind of giving you the indication that either the sensor data that we are getting, it's not providing the actual data, and it's kind of giving the control signal to the control system. This is again for the outdoor sensor and the ventilation system. You can see it's kind of need more time to detect, and at some point, like this fault is the data is the discrepancy is kind of quite big. And this is also kind of, you can see the hydroponic system when the fault is happening. So now this graph is kind of showing like what are the benefit of the fault detection and diagnosis from this research for greenhouse application. You can see like this graph is basically showing that if you don't integrate the fault detection and diagnosis tools, and this graph is kind of showing that how much cost you can kind of save if you integrate the fault detection and diagnosis tools. Now, again, also like if you have any false alarm like that generated from the algorithm, that will give also kind of the very high cost into the operation. So that's why you have to kind of have very accurate model to kind of predict the fault detection and diagnosis issue. And you can see, like they said, that use of fault detection and diagnosis method can reduce the loss of by almost by 70% with the integration of fault detection and diagnosis tool for the greenhouse application. This is also another research from the Cornell's, like they try to use the fit-for neural network models to kind of identify the 4 different faults: the actuator fault, mechanical fault of the hydroponic system, the pH sensor fault, and EC sensor fault. And you can see definitely like the EC and pH sensor fault could detect very early, like it's more accurately you can detect, like almost at more 100% time you can detect within very short time. But any kind of actuator fault, although the fault happened, but it needs more time to detect, like almost 6 hours. Some cases it's needed for 100% more accurate detection, need almost 13 hours. So within these 13 hours, like you can imagine, like if the actuator is not working perfectly, that can cause huge problem. And this chart is kind of showing that 4 different types of the fault. Like this is kind of showing the normal operation, and this is the first type of fault. You can see like after 40, the fault basically start, and definitely if the fault start, like it will continue. This is kind of showing the second types of the fault, like especially the mechanical fault. You can see like this is the normal operation, the top one, and this one giving the signals for the faulty data. This is for the EC sensor, sorry, the pH sensor. So this, in that case, this is the normal operation. But in that case, like if you just look at the fourth graph, you can see the different signal is giving from the control system. That's kind of giving an indication of the faulty operation of the pH sensor. And the last graph is kind of showing the fault detection for the electrical conductivity sensor. This is kind of the normal operation sensor. And the last one is kind of giving the indication that like when this fault happened, for example, in this case, this is the fault happened, then it's normal operation. And then again, you can see that very frequent fault is common for the electrical conductivity sensor. And this is kind of showing a complete nature of how the control system works. You can imagine this is a hydroponic system. You have plant, and this is the greenhouse. and that have different environmental control scheme and hydroponic control scheme. If you have a fault detection and diagnosis algorithm, it will give, okay, if it's the normal output, the conventional or the current, the control system that perfectly can works to provide the temperature, relative humidity, the water flow for the hydroponic system. But if any kind of fault is happen, definitely it will give the signal to the control system either what kind of fault is happening after doing the algorithm analysis about the fault diagnosis. For any kind of the plant fault that could be also detected with the machine learning algorithm, and based on that detection, you can kind of take the action in the control system to resolve that particular issue that's detected with the algorithm that developed for the system. This is now, I will just very quickly show you some research that we're trying to do. Like we're currently in our lab, we're trying to analyze the electrical conductivity, pH sensor, and also the ion selective sensor fault. And in that, this is kind of showing our current experimental data, and we're trying to use the Raspberry Pi, Arduino to kind of collect the data. And this is kind of showing the different sensor that we're trying to analyze, like what kind of fault they can expect and what are the different factors that causing that fault. And this is kind of showing our the flow chart, like what are the different steps in the fault detection and diagnosis tools, like how we generate the data and how what kind of machine learning algorithm we're trying to use. And finally, we'll kind of integrated that things in our control system to make the control system more precise and accurate, and also kind of avoid any kind of the problem that could happen if we don't detect that fault in the sensor or other control system. And this is kind of showing a complete picture, like how these things works, like based on the data, it will kind of definitely develop the different algorithm using the machine learning algorithm. And it will give the normal data or the different types of fault, either actuator fault, sensor fault. And also it will visualize like what kind of fault is that. And based on that, the signals from the control system, the growers can use either apps or some other control system to get the signal that that particular sensor need replacement or the need calibration, or any other things like any hydroponic system, either a pump or it could be the other actuators that's kind of not working perfectly, and they can take some action based on that the alarm or the signals they can expect into the control system. And that's kind of everything's like from my set, and I think